you'll end up having a hardness value, which is correlated to strength, and a toughness value. We'll have two different levels of carbon, percent carbon. We'll have two different heat treat temperatures. We'll have two different cooling rates. We'll have samples that have only carbon as the alloying element, and samples that have other things that improve the effectiveness of the quench, for lack of a better word. And we'll have 3 samples at every setting. So not a lot of duplication, but a little. And so each of you individually are going to do this test of your sample. And in groups of 3, you're going to write the report, unless somebody wants to write it independently, and that's okay, but I'm just giving you that option. And the report is going to be about everybody's data. All right? So we're meeting for the lab on Tuesday and on Friday. On Tuesday, just heat treatment, literally taking your sample out of the furnace, throwing it in water, or setting it on a brick to air cool and then throwing it in water. I got a half hour for 6 people. It won't take that long. That's all your commitment is for Friday, or for Tuesday. Then Friday, we'll do the toughness and hardness test. Again, each person's going to do their own, and I'll have a Google Sheets that we put all the data up on. Okay? So part of this exercise is dealing with data, because you'll maybe probably have data that doesn't seem to fit, and you'll, as a group, need to justify why you might throw out some data. And we'll talk about that. So that's next Tuesday and Friday. Tuesday of the following week, I want each group to give me their procedure section. And you'll have, I might have already put it up, but you'll have this is what goes in this section, these are the questions to answer. This is what goes in this section. I mean, very set out what you need to do in each section, what the graph should look like, what's the x-axis, what's the y-axis, everything. But the procedure part, I want you to get to me by that Tuesday, mostly so I can look it over and say, oh, you forgot to add this, and then that's the hardest part. Once you get that written, then doing the report tends to be pretty easy. But that seems to be like a block, an obstacle that sometimes keeps people from getting the report done. The report isn't due until the final exam. Okay? So that's lab. I know that the samples are arriving on Monday, so I'll be able to prep them, and we'll be able to do lab next week. We won't meet for class. Okay? So this is, right now we're in 9th week? Right now we're in 8th week? Okay, so that's 9th week is the lab. Then 10th week, Tuesday we'll talk about the lab, then we have topics that are totally what the lab's about, so you have an idea about what you should say. And then Friday, actually it's just Tuesday of that week that we'll do that, and then Friday we'll have the optional exam, and then the following Tuesday will be kind of review, a little bit of polymers. Okay? So if you're thinking about what's out in front of you, you have one homework that's due today. You have one more homework after that that's due at I believe I have it due at the final. You have that procedure part that's due, that's part of the lab grade, and you have the final exam. I think that's it. Any questions about what's out in front of us? Okay. So I had this crazy thing happen. I'm still kind of reeling from it. I have MS, and I also broke my shoulder 2 years ago. Had my shoulder joint replaced a year ago. No, maybe 9 months ago. And I'm kind of getting to the place where it should be pretty effective. I'm not really happy with it. And for whatever reason, the deltoid muscle and its attachment and the nerves in the deltoid and the MS are just conspiring and causing a lot of pain last week. And so last night I took a gummy. I knew you'd like this part of the story. I also have the THC lotion that I put on it. I think I tell myself it's gonna work so that I feel better, but pretty much it's mostly the ibuprofen and the Aleve that does the trick. Maybe a little, I'm lying. Tylenol doesn't do anything. So anyway, I had this just like amazing dream. And I don't know if it's the, yeah, you think it is. Well, I don't know. I got this book for my son, who is a public defender, who really kind of hates the cops, generally, who's a Kettering grad, it's about how the big bad wolf was framed in Three Little Pigs. He's very eager to read it. It's really funny. And it's really bizarre. So I think having had that book, read that book, and having had that gummy, I just had this incredible dream, which I'm sad to say is disappearing from my mind. Like when I woke up, it was like, oh my God, that was so amazing. It was sort of like that incredible dream where when you wake up, you're like, oh my gosh, I'm glad that was just a dream. Only in this case, it was like, oh my gosh, I'm glad that was just a dream. But wait, that was amazing. And it keeps drifting away. And why am I telling you this? Because since we're on the last few lectures, I can tell you I took a gummy. I mean, what are they gonna do, right? So the other thing I'd like to try, hopefully it won't bore you, but over these last few times that we meet, probably not in the lab, of giving you, I don't know, a gift, hopefully, here and there, maybe, I don't know what it would be, but just something that makes this class memorable, and I don't know, maybe it makes me memorable too. But also, let me just say that while it's good I don't have to use my left arm to write on the erase board, I am in mega pain with this left arm. So just be patient with me. All right, so we talked about the eutectic phase diagram, and you have a homework that's due today on the eutectic phase diagram. Before we go on, is there anything that seemed in the homework like I didn't talk about it, or you could use a refresher, or heck, what does this question mean in the homework? Anything at all? Lorenzo?
When the weight percent and the temperature is on the line,
yeah.
What phases are present?
So if you feel like it's a matter of choice, choose. And as long as you've shown where it is on the diagram, I'll know what you did. Ideally, my goal was to have the first one be in the off-eutectic, in the one-phase region, only for illustration purposes. But if that's not what you do, don't worry.
Yeah, I think it's a little bit to the right of the line.
Some would say it's to the right of the line. My goal was to get to kind of emulate what we did in lecture, right? But if you said, no, it's in the two-phase region, then totally fine, okay? You'd be amazed at how hard it is to find a composition that does exactly what you want to do at each of the temperatures so that we can make that comparison, okay? Any other questions? Okay, yeah.
Can you define proeutectic?
Proeutectic, okay, so if I have anything between here and here, or between here and here, hyper. Okay, so this only applies to those. So if anything that's over here won't have a proeutectic. Anything over here won't have a proeutectic. Of course, if I'm right at the eutectic composition, I also don't have a proeutectic. I only make eutectic, right? But if I'm somewhere between here and here, this liquid, as I come into this region, I'm starting to make alpha. alpha that I'm forming before the eutectic transformation. Pro before eutectic. And then when I cross here, anything that was liquid becomes eutectic. So I still have these areas of alpha, but where there was liquid, there's eutectic. There's this alternating layers of alpha and beta, right? So when I'm here, there's kind of two different alphas. They're the same composition, but they're in different parts of the microstructure. There's the alpha that formed pro ahead of the eutectic, these big areas. And there's the alpha that formed in the eutectic. So when I say, where's the alpha labeled, where's the pro-eutectic alpha, or the pro-eutectic phase? That's this, the rest would be eutectic. Okay? This isn't on your homework, but as I go, at this composition, I have 100% eutectic, yes? So as I move in that direction, away from the eutectic, then I'll have more and more of the pro-eutectic and less of the eutectic. Does that make sense? Here I have 100% eutectic. As I move in this direction, I have more and more pro-eutectic, less and less eutectic. Same as I move in that direction, only in this case, it's pro-eutectic beta. So I've got this alpha, these chunks of alpha, and then alpha in the eutectic. So it's kind of, two ways of looking at this. I have two different phases, right? Phase diagram, alpha and beta. I also have two different structures. I have pro-eutectic structure and eutectic structure. So the point of asking that question is for you to look at this in two different ways. Because that's what we will be doing with steel today. Does that make it clear? So I don't want to muddy it. Maybe this will make sense. When I'm right here, right there, I know the composition of the alpha, right? I know the composition of the pro-eutectic alpha. That's the composition of the pro-eutectic alpha here. What would the composition be of this eutectic structure? In weight percent, whatever this is. The composition of the pro-eutectic, when I'm just crossed, the composition of the pro-eutectic is right there. What's the composition overall of the eutectic? It might seem obvious which holds you back. It might seem like I have absolutely no idea which holds you back. If I'm here, what's the composition of my eutectic? Whatever this is. No matter where I am, that's the composition of the eutectic. Okay? No matter where I am, the composition of eutectic is whatever the composition is of eutectic when it forms. Okay? Now, the eutectic might have slightly different amounts of alpha and beta, but its overall composition is constant. Okay. Gave you more than you asked for. Any other questions? Yes?
Do you want us to turn this paper in with it too?
You mean the phase diagram?
Yeah.
Oh, just the whole paper? Only, I'm happy if you turn it in, because then it's all together when I give it back to you. I also want you to give it to me if it has calculations on it that you think might help if there's a mistake. Or if you're not sure that I would interpret what side of the line your alloy is at, and you want to make sure I know where you got that. Okay. All right, cool. Any other questions? Okay, so side was the off-detecting, right? Any of these compositions. And what happened there? I had liquid, I cool down, I start to make alpha in the liquid until I have all alpha. Continue to cool, it's all alpha, all alpha, all alpha, all alpha, all alpha. And now some beta is in the alpha. But that beta is not eutectic. That beta will find its way to the places of highest energy, which is where the grain boundaries are. So this guy will have these grains, and of course all this depends on magnification. These grains of alpha, and beta will form where more grains come together. So there might be some beta here, there will definitely be beta here. We've got 3 grains coming together. And that microstructure just is not very good. Because alpha and beta, one of them is brittle. We don't know, I mean, you would know at this point, but one of them is brittle. And so if the brittle material is beta, then when this thing is impacted, there'll be a crack that forms, and the crack will just follow like that. And if you looked at that surface under the microscope, it would be faceted, like the grains. That's if beta is brittle. If alpha is brittle, then somewhere there'll be a crack that forms. And it might have to change directions, but it will go right across. And that fracture, I show it being zigzag, that fracture is actually much more flat. Looks like they call it glassy. In either case, not a good material for brittle, any kind of toughness application, and the same would be true over here. So aluminum alloys have this problem. We love to use aluminum alloys because they're lightweight, but there's a limited amount of whatever this is, aluminum or copper, there's a limited amount that I can get in each side. And in either case, the high aluminum phase is going to be brittle as opposed to the high copper phase. So, and yet we like to use aluminum, we'd like to make it a useful material. And so the process that we use with the off-eutectic in aluminum is called precipitation strengthening. So, use some mirrors that way, send them that way, and bring me back what's left. Oh, give me one. You know, I was diagnosed with MS in 2003. Everybody I knew had a nephew who could give me some weed. It was always a nephew. Oh, I got a nephew. Oh, let me talk to my nephew. My nephew could give you some marijuana and make it a lot better. But it was so bizarre because it was like, it's always the nephew. I have that fear of losing control, so I just didn't want to try that. But the gummy is helping. All right, so on one side of this is a pretty, actually, typical phase diagram. So far, you've seen some pretty basic, simple phase diagrams. This is the copper aluminum phase diagram. And the left side is kind of like what you're used to, and there's a eutectic right there at just about maybe 33 weight percent copper. Notice these temperatures in Kelvin. But over here, whew, we've got, well, this is actually alpha, the aluminum, mostly aluminum phase is the alpha, that we've got, you know, oh my gosh, I don't even know, 20 phases or something on this phase diagram. The arrows, in some places, are kind of difficult to know exactly what they're pointing at, but my point in showing you this is there's all these regions that are single phase regions, and between them are two phase regions. So even though it looks really complicated, if I said, all right, let's look at 873 degrees K and 76 weight percent aluminum. So see if you can find that place.
What temperature?
Let's make it a little warmer. Let's say 973, might be a bit too high, but I think that works. Let's say 973, and then I wanted to direct you to where the arrow is pointing to eta, or I think, no, that might be a sigma. No, that's an eta. Eta 2. See where that's pointed, eta 2? So 973, let's call it, yeah, 77 weight percent copper. You see that area that I'm sort of pointing toward? So, again, this looks like, oh my gosh, this is such a complicated phase diagram, but don't let the look intimidate you. So I've got something kind of like that. And this is eta 2, and that's liquid. Now you see where I am? And I was pointing you toward someplace like about there. All right? So I want to look there, and I want to look there. First point here. Phases present. At point 1. What are the phases present? The arrow's telling you. Theta 2, right? So at point 1, phase is present, just 1. What's the composition of that phase? I think I said 77? Yeah? Didn't I tell you 77 weight percent carbon? You're with me. Did you all have a gummy?
Maybe.
The composition, so eta 2 has 77 weight percent copper. Because I told you that. Or because you read straight down to read it. What's the relative amount of eta 2? Not the composition, we got that. What's the relative amount? 100%. There's only one phase, right? All right, now let's look at point number 2. And imagine the point is about that distance between those two sides. What phases are there? We're in a two-phase region between two single phases. What phases are present at point 2? If it wasn't labeled, which actually it isn't labeled, so this is good. Between each single phase region and the next one is a two-phase region that has both of those phases. So in this area right here, just to the left of the eta 2 region, which has liquid on the left and eta 2 on the right, so in here, the phases are eta 2 and liquid, right? What's the composition of the eta 2 and what's the composition of the liquid?
Maybe two is like 73%.
Say that?
Like 73%.
27.3%?
No, A2 is like 73%.
73% or weight percent?
Weight percent, sorry.
Weight percent what?
Copper
Very good. And that's for which set phase?
for.
Which one? I mean, either one, you just tell me.
For eta.
That's eta 2,
Yeah,
okay.
so-
So eta 2 has 73 weight percent copper, okay? And what's the composition of the liquid?
Or weight percent.
Does that sound right to everybody? About 62, okay? So what we're saying is that this is 73 and this is 62. Yeah? And what would you, roughly, what would you say the composition of the steel is at this point? What is this? Anybody? Well, it's about 2/3 of the way in difference. I mean, I didn't define it, so we can right now. Let's see if there's it's about what, 11? So let's say it's maybe 8 more, so we'll call this, maybe call this 70. Is that fair? Yep. All right, so somebody give me an equation for the percent, not weight percent, for the percent eta 2. Who wants to give me that equation, that percent eta 2? This is all you did over and over again in this homework. Just, Jacob. D. Yeah.
So for that one, it would be your eta 2, so is it 73? Wait, I think they're written down here. So would it be 62? Is that your 62?
That's fine, you just tell me, I'll write it down.
Yeah, 62 minus R, was it 77? Wait. What makes these equations? I think which one.
So this is my lever right here.
Mhm.
And 73 and 62, and my fulcrum is at 70 with eta 2.
Oh,
This is liquid. Go ahead.
so is it 73 minus 62 over 73 minus 70?
Ellen?
It should be 70 minus 62 over 73 minus 62.
Anybody have another alternative? Okay, well, first of all, the denominator should be the whole length. Okay, so this is correct. Now, 70 minus 73 or 73 minus 70, this side length tells me about the percentage of this over here. Always on the opposite side. All right? So 73 minus 70 over 73 minus 62, that would be the percent liquid.
Okay.
Okay? Now, even though this is an incredibly complicated phase diagram, the method that we use is the same. So if I gave you a point, if I put a point on there and I put a letter X next to it and I said, look at point X and tell me what are the phases, what are their compositions, what are the relative amounts, that point will either be in a single phase region, where there's just one phase, the composition of the phase is the composition overall, and it's 100% of that phase. Or it'll be a two-phase region, and the composition of each phase will be the endpoints of the isotherm line. And you'll use the lever rule to get the relative amounts of each. And that's true for a eutectic phase diagram, even a really complicated one. Okay? Now, this really complicated phase diagram is the aluminum alloy phase diagram most often, where copper is added to aluminum. And we're really only dealing with the very far left side of this phase diagram, which happens to be part of a eutectic. But there are a couple of other, I think there are a couple of other eutectics on here. Let's see. You might be able to find beta 2 on cooling, and that's when beta 2 is, let's say 76. Goes to, oh, how did I make that up? Whatever that is, 2 plus delta. So that looks like, this goes here. That sort of looks like that, where here's my eta 2, and over here is that, whatever that is, and over here is the delta. So that's a eutectic. Wherever you see a flat line and a V on top is a eutectic. Ah, no, wait, it's only a eutectic if it's a liquid, it's going to two solids, right? In this case, I got a solid going to two solids. So it's like a eutectic, it's called a eutectoid, being like a eutectic. So eutectic is a liquid going to two solids, and a eutectoid is a solid going to two solids. Let's see, are there any other eutectics? Yeah, there's a good one. All right, this is a eutectoid. Beta at, I'm going to say 86% copper. When cooled, I have to get the temperature. So over here, this was around 850. And here, beta, it's 840. that beta transforms to gamma 1 at, we'll say maybe 83 plus beta, what's not labeled? Oh, yeah. That's technically that ought to be beta. They call it just plain copper. So the phase on the far left, shoot, it shouldn't be a beta, let's call it, is there a single gamma? No, we'll call it a gamma at 100, sorry, 90. So on the phase diagram, that very traditional detect away or detecting looking. This is, I said 83, this endpoint is 90, that's 83, there's beta, there's gamma 1 plus gamma, so this is gamma and this is gamma, something like that. All right? So you could get a really, really freaky looking phase diagram and I could just say, write one of the eutectic or eutectoid reactions. Pretty simple. Yeah? Eutectic, liquid goes to 2 solids. Eutectoid, solid goes to 2 solids. Now there's 2 other reactions, transitions in phase diagrams that I just want to point out, but it's not on a test or anything. But there are times when we have a transformation that looks like that. And sometimes this is liquid plus a solid, and then this is a separate solid. And sometimes it's 2 different solids transforming to a 3rd solid. So there's a lot of those. If you look, you see a lot of upside down V's. Those are all eutectics or eutectoid or paratectic. Tick, if it's a tick, that means there's a liquid. And paratectoid. You don't need to remember that. I'm just pointing it out in case paratectoid. In case you see those and you're like, I wonder what those are. Because what's unique about each of these points is that it's a place where 3 phases can be all at one time together. Okay? All right, so that said, if we look over on the left, I don't know why they moved the label names around, because that should be alpha. So let's just pretend it is. So here's my far left side of my copper aluminum phase diagram. This is kind of like that. This is this. And all we care about really is this area here. This is, we're going to call this alpha and theta. There's liquid up here, so this is alpha plus liquid. Okay? So, under equilibrium conditions, that means slow cooling. If I'm thinking about what do I have there? What do I expect to have there? If I cool slowly to that point, I have theta phase has precipitated at the alpha grain boundary.
Is that inferior? Could be. Why? Why is that inferior? Ellen?
Because when it cools, it'll become solid alpha and then eventually get some beta in there, but it won't form a eutectic structure, it's kind of like.
Right, there's no eutectic structure, and I create an opportunity for long areas or larger areas of the brittle material, whichever it is. Okay. So we can instead do precipitation strengthening. Which is sometimes referred to as age hardening. Now we're talking heat treatment. So everything up until now that we talked about, it hasn't really mattered how we cooled down. Heat treatment is heat treatment. It's really heat treatment only if the cooling rate is important to what you make. And in this case, it is. The cooling rate is important to what you form. So there's 3 steps. Step 1, solution items. In the case of the aluminum alloy, that means heat into the alpha region. And allow for equilibrium. All right, so we know we have equilibrium if the composition is the same everywhere. The weight percent copper is the same everywhere. That's step 1. So that might be heating to here. You can keep these pens. And that might be like here. Well into that single phase region, holding it there until all it does alpha, and the composition is the same throughout. Step 2 is quench. And we want to quench deep into the two-phase region. So deep or so cold that there isn't enough energy or in this case the theta phase to form. Remember that that would require diffusion, and if it's cold enough, maybe that diffusion can't happen. And so what we have is a supersaturated alpha. Not stable, very high energy. just hoping to get enough energy to be able to decompose into data. And so that might be,
Bless you.
there. That should be a straight line. Okay, third step, and this is the step where everything happens, this is why it's called age hardening. The third step is called aging. Solutionize, quench, age. Heat within two-phase region until warm enough for theta to precipitate. As particles. Distributed throughout so that would be leading to there. All right, so you're given some temperature ranges for that solutionizing. It kind of depends on the composition, but somewhere between 450 and 550 roughly. So that's what, 450 plus 273, 650, 673, 723. So that's about 723K on here to 823K. Then quench, and quenching typically is just room temperature for aluminum alloys. And then the aging temperature kind of depends on what your composition is, but it's kind of up into here. It's still a ways away from the solvus. And after the aging's over, then you cool it back down, but we don't really call that quenching because we just want to stop that. That means everything's old. All right? So there's a graph here at the bottom that shows you how the hardness changes once we start aging. So the very far left, that's when we just have our supersaturated solution. And then we age, we see the hardness, the strength go up until we have this peak, which is the perfect distribution in size of those particles. And then we overage, meaning those particles start to get too big, or start to get bigger and the hardness drops. okay? So, aging here. So the harness starts to rise and then fall. That might be aging temperature 1. Typically, if I go with a lower temperature, this thing takes a lot longer, but I get a higher ultimate harness. Now, this is a log scale, so the difference between T1 and T2 might not be big, but this time at maximum strength could be days different. But obviously, we want to try and get our best of the best, and so we're going to shoot for a temperature that gives us the highest maximum, but that doesn't take too long to be practical. Okay? So that's our first 2-phase heat treatment. Now, all of the things we talked about already about strengthening mechanisms, like solid solution strengthening, point defects, we have that here. We have copper added to aluminum. So we have a strengthening because of the alloy. And now we also have strengthening because of the distribution and size of the second phase. And just like before, it's all about creating obstacles to dislocations. So if I have a lot of tiny particles, I have more obstacles. But with time, those are just going to get coarse, and they're not going to stop as many obstacles. All right? So we have one more strengthening mechanism, and that's the mechanism we use with steel. Let me make sure I've got everything I wanted to talk about here. So we'll take a break. At least a week ago, maybe a week and a half ago, I handed you want to have that one. The first, there's a door here. I don't know if anybody has the key anymore. And then there's a door here. You're going to come in this door for lab. So this is the furnace. And it's labeled metallurgy lab by the door. That's where we'll meet Tuesday. And then Friday, we'll meet way up here. I'm trying to remember what they labeled this as, because it's been a lot of different things. But there's a big, huge open area where we have the robotic CNC and a bunch of other equipment. And there's a little room within that room that has hardness testers. That's where we'll meet on Friday. Now we've got hardness testers in here, but they're not nearly as well calibrated, so I like to sneak in and use those. So we'll start there on Friday, we'll start here on Tuesday. Once we do the hardness test, we'll come back in here because this is where the impact tester is also. But doing the impact test will deform your samples such that they might not be as easy to get hardness tests out of. Okay? And I'll create a Google Sheet for the data. I probably will also just make a matrix on the dry erase board in that room for you to put your data, just because it's for whatever reason, sometimes people just never ever get around to putting their data on a Google Sheet. So I might just set it in there so that we're sure we get everybody's data. All right? Some of those rooms, I don't remember what the numbers are. This is the first room I taught in every 3 years ago. This class, actually. But, and other than 1815, 1817, 1819, and a couple other rooms, I've pretty much been in this room or that room, probably 80% of the time. So, a year ago? Let's see, no, this winter. We're in here, it's about the coldest day, and the fire alarm goes off. Were you here then? Yeah, I guess it was
I
A
wasn't-
section.
I mean, I wasn't here, but I was, yeah.
Or was it B section? It was A section.
It was A section during. It was one of the coldest days. Yeah.
Was that?
I can't remember. It was
I thought it was A section, but
It was
maybe
A
not.
section.
It was.
The fire alarm went off because.
Yeah, fire alarm went off because
Surprise.
in some of the rooms behind the foundry, which is on the other side over here, for whatever reason, somebody thought, oh, well, we're gonna be moving rooms around. Let's just take all this insulation off of these pipes here, because it's not that important. And those pipes had tended to be somewhat exposed to the wall, and they burst. And when there's a drop in water pressure at Kettering University, the fire alarms go off. It's just a trigger because that could be a reason why the water pressure would drop. As a matter of fact, I'm learning that back in the 50s, there was like this competition. How can we make the water pressure drop so that the alarms go off? So that was a regular thing with Kettering students. But anyway,
Who won?
the alarm goes off. We go outside. It is like the coldest. And you know, why not wear shorts? Because you're going to be inside. And we're out there a long time. And I'm thinking, this is not a drill. Not today, not at this temperature. This is not a drill. Finally, after like 45 minutes, the alarm goes off. And we open the door to come back in, and this is flooded. And that is flooded, that hallway. But these seats aren't. So I think we can have class. Everybody's like taking pictures and posting it on their whatever, and I'm like, come on, we can have class. And they're looking at me like, are you kidding me? We're not having class, not like this. The campus safety person thought I might get electrocuted.
Huh?
Standing in the water. Anyway, it's amazing to me that they happened to find the exact same color and style of carpet. And it was old carpet, but it looked just like this. Anyway, where was I? Oh, okay, so that's where we're gonna meet, and now we're ready for our iron carbon phase diagram.
They replaced the carpet?
Oh, yeah, oh, they had to.
Mold.
You don't think they did?
No, I didn't notice.
I guess
I was in Hargrove's next door.
I assumed they did. They didn't have this room open for like a month,
Yeah.
so maybe they just tried it. You know? That stain was there. You're right.
Yeah. I can say if they replaced it, they did a good job, but.
The water might have cleaned it.
Yeah, whatever. This is like one of the last times I'm teaching in this room, so. Basically,
Who won the? Not won, but like who was able to pull the fire alarm the most during the 50s? I guess. With,
oh, how, they didn't pull the fire alarm.
No. Yeah, they
Cause
triggered
it to happen?
caused it with the water pressure to drop.
I do believe it was one of the floors in the residence hall. It wasn't one of the fraternities. They tried,
Oh.
but one of the floors in the residence, it's not something they did there, but they figured out a way to cause water. No, they turned all of the showers and the faucets on in the dorm
Okay.
at once.
Please don't do that, guys.
Yes, this is our RA. Please don't try that again.
Please.
Well, and you all appreciate the value of water. I mean, back in the 50s, we didn't realize that it was a limited resource, and I think yeah. Okay. So. So the iron carbon phase diagram, you notice On the bottom, it doesn't go from 0 to 100 weight percent carbon. It goes from 0 to not even 7 weight percent carbon. So we're looking at just a fraction of that whole phase diagram. Back in the day that I had to memorize this, everything was in degrees Fahrenheit. All right, so we got a temperature here. 727 C. I don't know what this guy called it. Yep, something good. But this isn't to scale issue. Let's make 737 there. And then we go up to, this is 912. And this goes like so. I'm going to call this 0.77. They call it 0.76. I've seen phase diagrams that call it 0.8. When I learned this phase diagram from 0.77, and that author won't change your answers too terribly much. This point right here, I always call it 0.02. I've seen 0.022, 0.025. Again, it's really not going to change your answers too much. Okay, so then at 14, C, we go up, down again. And this is, maybe not quite that far. 94 and 1538. All right, and then this comes. Let's see. Let's go up here. Call that 47. And then that connects to. Okay, that's good. All right. So this tiny little place here, that's alpha iron. It's called ferrite. And it's BCC. And it can only hold or dissolve, I forget that word. Up to 0.02%. Then this way over here is a compound called cementite. is Fe3C. It is a carbide. It's a complicated crystal structure. Dissolves, that's like this, yeah. Dissolves. 6.7% carbon at all temperatures. It is an iron carbide, but it's not that iron carbide. It's not an iron carbide that we think of with tool steels. And so we don't usually call it iron carbide, we usually refer to it as cementite. And so if this is alpha, and this is cementite, then in here is all two-phase alpha plus cementite. This is clearly not to scale. And this whole big area here is gamma iron. It's called austenite. Or sometimes gamma iron, and it's FCC. And it can dissolve a lot more carbon. And right here, this is delta iron. And it is BCC. So that this region in here then is alpha plus gamma. And this is gamma plus cementite. And this is delta plus gamma. There's liquid. Gamma plus liquid. Delta plus liquid. And we don't need to, well, we really don't need to worry about beyond there. So what phases do we not have? Alpha, cementite, gamma, and delta. All right, so we're thinking about Fe3C. There's 3 irons. Anybody know off the top of your head the atomic weight of iron? Yes, there is that. That I want to take that home. No, I don't actually.
55, I think.
All right, so where is iron? Right in the middle, number 26. 55.85 grams per mole. And then it's got 1 carbon. What's the atomic weight of carbon? Can't think of it. It's number 6. 12.01. So one compound, one unit, would weigh 3 times 55.85 plus 12.01. So what is that per wall? Total of 179.56, close to 180. By weight. And so the composition of cementite by weight would be 12.01 divided by 179.6 weight percent carbon. Which hopefully still is 6.7. Yep, 6.68 weight percent carbon. So that's where that 6% comes, 6.7 comes from. Doesn't matter what temperature it is, it's just a compound. It has the same composition at all temperatures. If I had a piece of pure iron at room temperature, it would be alpha iron. If I heated that alpha iron up until I got to 912C, it would change from alpha iron to gamma iron. It would change from ferrite to austenite. It would completely change crystal structures. Do you happen to remember which of those two is the highest packed? One of them had a higher density than the other. And don't use strength to help decide. Well, let's see, FCC was 11.3 and BCC was 10.4 in that atomic packing factor. So more atom per unit volume for FCC, meaning it's denser, meaning the atoms can get closer together. So when it goes from being BCC to FCC, it shrinks, right? And then when it goes from that back to BCC, it expands. And the shrinking and expansion isn't small, it's like 8%. You probably can still on YouTube maybe see a video of a piece of wire across 2 sides of a furnace. And it's kind of limp, BCC, get high enough at one temperature, it shrinks to FCC. And then it expands again when it gets to delta. Still, this is all solid, even at 1500 degrees Celsius. Still solid, cherry red solid. I think I can find you a phase diagram that has the temperatures, but then it also has the colors. Because back early metallurgy, that's what they looked for, were particular colors to know what phase and where you were in your heat treatment. Okay. So here's a puzzle. FCC is closer, the atoms are closer together than BCC. How is it that FCC can hold 2% carbon and BCC can only hold 0.02% carbon? 100 times more carbon atoms can get in this FCC than in that BCC. The FCC has less empty space than BCC. And yet we can get a lot more carbon in there. And the reason is that the space, while it's less, there's more places where there's a bigger amount of space. Less overall space, but the space is in bigger chunks, let's say. BCC has more space, but it's in tiny little spaces that carbon couldn't fit. So a couple of contradictions there, right? FCC is softer, and yet it's denser. FCC is tighter bound, and yet you can get more carbon in it. And if you can get more carbon in it, even though it's FCC, it could be harder than BCC because you can add carbon. So just a couple of, like, it's good to have rules of thumb. It's really good to have rules of thumb, but there are a couple contradictions here with FCC and BCC iron. All right, now, given that whole big phase diagram, the part of this phase diagram that we will be dealing with, that metallurgists in steel deal with, is like, actually not even there. Well, all right. Just that. The rest, we don't even care about. We're only going to be looking at just that piece of it for heat treatment. 4.3 weight % carbon, that's cast iron. So this over here, we're talking about so much carbon, it's not an engineering material. So what do I have here? I have, put it right here. I have gamma at 0.77 weight % carbon when it's cooled through 727 degrees C, transforms to alpha iron with 0.02 weight % carbon plus cementite with 6.7 carbon. What did I just write? What is that? Transformation. Looks kind of like one that we've probably written where we have a solid on cooling goes to two solids. What's that? Liquid on cooling goes to solid 1 plus solid 2. That was a eutectic. Solid going to solid 2, solid 3, where I have all solids. That's a eutectoid, where there's all solids. So this transformation in steel is a eutectoid transformation. Everything about heat treating steels has to do with that transformation. This would be the eutectoid microstructure. The eutectoid microstructure is alternating layers of ferrite and cementite. Looks quite a lot like that. eutectic, or one of the eutectic microstructures, the one that we looked at. Alternating layers of this black and white, and that's black and white just because of how it takes the etchant. And it has a name, and that name is perlite. Eutectoid microstructure is called perlite. Not a phase, but an important microstructure. So we have a name when we refer to that. It's called perlite because of a material called mother of pearl, which maybe somebody knows of. Okay, good. I sort of assume everybody knew that. Well, it's because they did 33 years ago, but mother of pearl is the inside of an oyster, nice big oyster shell.
Oh.
And it has that sort of opalescent, 2 layers, kind of fingerprintish looking. That's why it was named perlite. You can imagine why cementite might have been named cementite. Very brittle, very hard. Ferrite is why it's Fe up here. Okay, so if I just only look at the part of the phase diagram that we really care about for the rest of the term, and this is not going to be to scale, just so that it's easier to see everything. That's the part that we care about. And really not much to the right of 0.77. So if we think about when we were talking about eutectic, we have a eutectoid composition, we have a eutectoid steel. .77 weight percent carbon. Typically, if you buy that steel, it's a 1080. That will, no, it's that, well, no, we wanted this to. We have off eutectoid steels. And those are strengthened using precipitation strengthening, talked about earlier. And then these are hypo eutectic steels, which are all of the steels, engineering steels that you deal with. Hyper-eutectoid steels are rare, they're brittle, we won't be talking about them. So we've got eutectoid steel, one, and the hypo-eutectoid steel, those are the two that we're going to talk about in the same way that we've been talking about the eutectic, where we're going to cool, and we're going to talk about what we expect to find at different temperatures. So in the lab, you're going to be working with a steel that has 0.18 weight percent carbon, so that's 0.77, that's 0.02, so we'll make it up there. There's one steel that will be here, and there's one steel that will be here. 0.18, sometimes we'll just call it 0.2, and 0.4. or sometimes 0.45, depending on the steel. So really, that's the only compositions that we'll look at. Tectoid composition, a 1018 or thereabouts, a 1040 or 45. You'll be looking at 1018 steel from the lab. When the 10 means just carbon, that's the only thing that is used as an alloying element. You'll also be dealing with 1045 steel, also plain carbon steel. But we can compare those two, knowing that they only have carbon, the only difference is the amount of carbon. And then we also have a 4140 steel. That's an alloy steel. So for the lab experiment, we can compare, you can see the effect of percent carbon for those two. And we can see the effect of alloying elements, because the carbon is about the same with these two. Different heat treatments. We're going to be heat treating those. It should end up being where we're heat treating it around there and around there. So this is about 1400 Fahrenheit and 16 to 1650. We're going to heat those steels to one of these two temperatures and then water quench. So heating this 1018 to 1650, I'm going to have all gamma. Heating it to 1450, I'm going to have gamma and alpha, protectoid alpha. But my 1040, 1045, both temperatures will be all gamma. We should see a difference when we compare this and this to our ultimate product. And then, of course, we're going to heat to those, and then we're going to quench. And there's another set of diagrams that we'll use not next week, the week after, that predict which non-equilibrium structures that we can get. So let me just give you the names of those, and then we'll go for today. So the equilibrium structures are the phases: ferrite, cementite, austenite, and the microstructure pearlite. The non-equilibrium structures but non-equilibrium means we have to quench to get them. The first is called bainite. If we cool so fast that there's not time for carbon to diffuse into layers, like in perlite, it instead diffuses into something like needles. So when gamma is quenched too fast, for it to carbon to diffuse form perlite. instead needles of cementite form in the ferrite. Now they're tiny, so it's a much smaller distribution of that hard phase, and so bainite is harder and stronger than perlite because of that. The other non-equilibrium structure is called martensite. Martensite forms when there's no time for diffusion. Supersaturated gamma crystals instantaneously fracture into another
I don't know what that is.
crystal structure. And that is even harder and stronger than bainite. So this is diffusion free or diffusionless. So it's instantaneous. Bainite formation is still diffusion. So it takes time. So gamma could form, if it's quenched, for bainite or martensite. Gamma can form one other thing, which I've already talked about. What's the other thing that gamma can transform into? Besides bainite and martensite. Perlite. So basically the goal of heat treating steel is to quench it too fast for it to form perlite. To skip the formation of perlite, to avoid the formation of perlite, so that you can get these harder microstructures. For some steels, that means you have to get them from what, I'm trying to do the conversion from Fahrenheit in my head. Say 900 C to room temperature in half a second. Not likely, right? Unless we're quenching razor blades, maybe. So some steels, you just can't cool them fast enough to get martensite. Some steels, you can take your time. You can cool them in air and still get that hardest form of steel. And the characteristic of these two is a characteristic called hardenability. Hardenability of a steel is the ease with which you can form the hardest form of steel. Or how likely is it that you can get that? Or how deep into the steel can you get that? Or how likely is it that you could quench an oil and avoid getting cracks by cooling slower? Hardenability. And so, turns out that 4140 steel, that third steel that we're dealing with, is a high hardenability steel. Not necessarily a high hardness, but a high hardenability. So this experiment that we're doing, this lab experiment, is about things that affect the hardness or strength of a steel and things that affect the hardenability of a steel. Okay. Watch your email. I mean, should this stuff not come on Monday, then we're gonna have to do another shift. So watch your email, but if you don't hear from me, well, I'll probably send something anyway, but watch your email. It's possible that we'll be here for the whole time and not just the 30 minutes that you got, okay? So don't make plans for the rest of that time yet.